Alright, here we have lecture 4.5, the very last lecture in college algebra. We are now at the conclusion of the course. This corresponds to section 6.7 from the textbook. So if you need additional reading materials or additional examples, highly recommend you check out that section from the textbook. We're going to look at several modeling applications for exponential and logarithmic functions, and we'll start off with the exponential modeling. So we've got exponential growth in the form of doubling time and exponential decay in the form of half-life. And the models are given there. Looking at the doubling time model, if we have a quantity that's doubling every d units, so if you have a quantity that's doubling every 2 hours, or doubling every 2 months, or doubling every 10 years, something to that effect, you'll be using the doubling time model. And this is where that doubling time is a constant. And doubling time is a constant. The initial quantity, as seen there, is a constant. T is the variable. And it's very, very important that your time and doubling time are in the same unit for this model to behave correctly. So in other words, if your doubling time is in years, your variable is in years. If the doubling time is in seconds, the variable is in seconds. So you just want to make sure you're paying attention to your units of time. Same thing with half-life. Half-life is a very similar concept, just decaying instead of growing. So half-life is quite famous for radioactive decay and is frequent there. And you'll notice that the two functions look very similar. The only difference is that negative sign there in the half-life model. So don't forget that negative sign in the exponent, because that's what gives the half part of the half-life model. And then flipping on over, we have one more model we'll be using. That's the relative rate model. Now what's cool about the relative rate model is its flexibility. It can be used for growth or decay. Whereas doubling time is growth only, half-life is decay only, relative rate can work for either. So there it's based off the natural exponential function, as you can see. And if that r constant is positive, you got growth. If that r constant is negative, you got decay. Alright, let's go ahead and play with some of these models. So suppose we got a rabbit population. I got 320 rabbits on an island. They're doubling every 5 months. So keyword there is doubling. That tells us, well, not just doubling, but doubling every 5 months. So that tells us the doubling time. If we know the doubling time, we can use a doubling time model. So doubling time model says quantity of rabbits at time t equals the initial quantity, which is 320, times 2 raised to the t over d. D stands for doubling time, which we know to be 5. So essentially what this function is telling us is how many times do we multiply by 2. So for every multiple of 5, we're going to multiply the initial quantity by 2 because it doubles every 5 months. Now, what's cool about this model is it doesn't have to be multiples of 5. We can use the model regardless. Suppose we want to know the quantity at 3 months. So set t to 3, so quantity at 3 months equals 320 times 2 raised to the 3/5. So we set the time value to 3. And that will not be a rational value. Let's go ahead and punch it into the calculator. Now we get approximately 485 rabbits. Now this makes sense. If the population is doubling every 5 months, it hasn't doubled yet. So at 5 months, it's going to go from 320 to 640. It will have doubled. So I know our answer is going to be somewhere between 320 and between 320 and 640. That's exactly what we see. Now, in part C, we need to be very careful that we're paying attention to our units. Approximate the population in 1 year. Notice our doubling time is in months, so our time variable is also in months. So we don't want to input 1. If we input 1 into the function, we're going to get the population after 1 month. We want to know it after 1 year, which is 12 months, so what we have to punch in is 12. So it's 320 times 2 raised to the 12/5. Alright, so it's going to be somewhere above 1200. And we get 1688, rounding to the nearest rabbit, 1689. Going off this model. Now, when will the population reach 700? So, quantity is a function of time. In the previous two problems, we were provided a time value and plugged it in. Here we're provided a quantity value and need to solve for time. So we set the quantity value to 700 into our function. And what we need to do is now go ahead and solve that. So we can go ahead and divide both sides by 320. And again, this comes from, using our function in part A. We just plugged in 700 for the quantity. So that's 2.1875 equals 2 raised to the t fifth. So let's go ahead and change that to a logarithm. So it's log base 2 of 2.1875 equals t fifths. And so multiply both sides by 5. Alright, so that's the exact answer. But suppose we want to round that. We want to know, okay, how many months is that? And let's, give us an approximation here. Because if we're just talking and I ask you, hey, when is the rabbit population going to hit 700? And you say, oh, no problem. It'll reach 700 at 5 log base 2 of 2.1875 months. I'm just going to stare at you like you're a crazy creature. English, please. So let's go ahead and round this. So some of you have a calculator where you can just type that in as you see it. Others, you might have to use that change of base formula, which we talked about 2 lectures ago. But let's go ahead and type that into the calculator. And we get 5.65 approximately. Just shy of 6 months is how long it'll take. Again, if it starts at 320 and it's doubling every 5 months, well, 5 months, it's going to be at 640. It's almost to 700 already. So that answer seems to make sense. Now, just a heads up, on the exam, I will ask for both. Right? I'll want the decimal approximation and the exact answer. So make sure you are showing both on the written portion of the exam. And last part, compute a relative rate model. Well, let's go ahead and do that. So here's our model. Quantity at time t equals 320 times 2 raised to the t over d. But suppose we want to change from a doubling time model to a relative rate model. So the relative rate model is this. E to the RT. So the good news is we know the initial quantity. That's still 320. That hasn't changed. What we need, though, is to figure out that relative rate. Now, I know it's positive because its population is growing. So what we have to do is plug in known data. And solve for that unknown value. So now we can't plug in a time value of 0 because that will just zero out the exponential, which we don't want. What we need to do is plug in a non-zero input. So I know that the quantity of rabbits is going to be at 640 when the time value is at 5. Right? Because at 5 months, it's going to be double. Oh, well, there's our equation. We can go ahead and solve that. So we'll divide both sides by 320. That gets us 2 equals e to the 5r. Switch it to a logarithm. And divide by 5. So there's our relative rate, which is natural log of 2 divided by 5. Let's go ahead and round that, which is approximately 0.1386. So if we wanted to write a relative rate model, it will look like this. 0.1386 t. there we are. So it turns out this model is mathematically identical to the doubling time model. They actually display the same data. So you just want to make sure you're very comfortable switching back and forth, because a lot of times computer software will default to this natural exponential function, this related rate model. But maybe in your own hand computations you use the doubling time model. So you want to be able to convert between the two. Even though they look very different, they're actually the same exact model. Let's look at a radioactive isotope, a half-life example. So this is something you can expect to see in like a chemistry class or a chemistry type problem. Polonium-210 is a radioactive isotope that has a half-life of 140 days. Suppose you got a 300 milligram sample. Compute the remaining quantity after 200 days. Well, I need to go and write a function first. So our quantity at time t equals the initial quantity. Again, if you need to flip back to the formulas, go ahead and flip back to the formulas. There's initial quantity times 2 raised to the negative, don't miss that negative, t divided by the half-life, which is 140. So now that we have the function down, we can go ahead and put it to work. We want to compute how much is remaining after 200 days, so we set the time value to 200. So quantity at time 200 equals 300 times 2 raised to the negative 200 divided by 140. And from there, it's just a matter of punching buttons on our calculator. And we get approximately 111.45 grams. So that tells us after 200 days, we'd have a little over 111 grams left of our radioactive sample. Now, that does make sense. It's going to be half every 140 days. So after 140 days, we're going to be at 150 milligrams, right? Because it'll go from 300 to 150. That's the half part of half-life. We have gone beyond 140 days, which means it'll be less than 150 grams. And that's what our answer reflects. So it makes sense. So suppose we want to know, hey, when will it decay to 200 milligrams? So here we are given a quantity, not a time value. So we take our function. Let's go. Let me rewrite it down here. Our function is 300 times 2 raised to the negative t over 140. That's what is modeling our polonium-210. And we don't know the time, but we do know the quantity. That quantity is at 200 milligrams. And here we have it. We have an exponential equation we're going to have to solve. To solve an exponential equation, we're going to change it to a logarithm. First, we need to isolate, so we can divide both sides by 300. Then we're going to go ahead and change it to a logarithm. So that's log base 2 of 2/3 equals negative t over 140. Again, key skill set there, being able to change exponentials to logarithms. And then we want to get t by itself. So that's going to be negative 140 times log base 2 of 2/3. Just multiplying both sides by negative 140. And if we want to round that, we can go and type that into our calculator. And we get 81.89. So it'll take just under 82 days to decay down to 200 milligrams. Alright. And part C, same sample of polonium-210, just, I ran out of room on the page, so we're on the next page. So let me go ahead and rewrite the function. It was what? Let me flip back. It was what, 300 milligrams? Yeah, 300 milligrams with a half-life of 140 days to be specific. So this is a half-life model. Suppose we want to switch it to a related rate model. Right? Suppose we're writing a paper, and just for the sake of consistency, we want to use the same model for all of our samples. We're going to switch everything to a related rate model based on the natural exponential. So let's go ahead and change this on over. So we know the the initial quantity is 300. That doesn't change. Remember, a related rate model is not a base 2 exponential, it's a base e exponential times RT. Now, we need to figure out that R. So, we need to plug in data and solve for that rate. So, we know that it has a half-life at 140 days. So if I set that time value to 140, I'm going to have half. Well, half of what we started with anyways, which would be 150. So what I did there is plug in known data. I plugged in a known time and quantity value, and then we can solve for that unknown constant. So we can divide both sides by 300, which gives us 1/2. Go ahead and change it to a logarithm. Divide by the constant, and there we have it. So our related rate equals natural log of 1/2 divided by 140, which, if we want to type that into our calculator, is negative. Now, it should be negative because it's decaying. Remember, if it's decaying, that rate will be negative, and it's 0.00, let's see, it's 495. So if we wanted to write a related rate model, that will be quantity at time t equals 300 times e raised to the negative 0.00495 time. And there's our related rate model based on that related rate. So you can see why the related rate model is so nice, is we can switch any exponential model to a related rate model. Basically, we take any exponential you want, base 2, base 3, base anything, and change its base to whatever we want. Alright, so that's the exponential models. Let's look at some logarithmic scales. So logarithmic scales are useful whenever you have a quantity that varies over a large range. So there's lots of scales of measurement that use logarithms in them. Examples include the pH scale, which measures acidity, the Richter scale, used to measure earthquakes, decibel scale, which measures sound intensity or volume, light intensity is another example, information capacities, radiation. There are many scales of measurement that utilize logarithms. We'll look at probably what's one of the more famous ones, the pH scale. And what most people know pH measures acidity, but they don't know it has a logarithm baked into it. The pH scale states that pH of some solution equals negative log of H+, where H+ is the hydrogen ion concentration in moles per liter. Now, that hydrogen ion concentration is not going to be a nice number. If you've ever taken a chemistry class, you know that your ratios and numbers aren't always going to be super cooperative, right? A lot of times in math class, things are very artificial, and we get to play with pretty integers frequently, right? Nice pretty numbers all throughout math class. It's such a problem in math classes that when we get an ugly number, we assume a mistake has been made. We've been conditioned to work with integers, but if you've ever worked in a lab before or actually worked with nature, nature doesn't necessarily care whether you get an integer solution or not. So a lot of times when you're looking at hydrogen ion concentration, you're not going to get a nice number. So for example, you got a sample of blood that has a hydrogen ion concentration of 3.16 times 10 to the negative 8 moles per liter. Is that acidic? Is that basic? I don't know. What does that mean? Sounds like a bunch of gobbledygook. That's why logarithms can be very useful. If we slap a logarithm on some range of measurement, we can shrink it down to a much more manageable level. So let's go ahead and do that. So we don't know what the pH is, but we do know the hydrogen ion concentration, which is 3.16 times 10 to the negative 8. So we'll plug that in. Notice there's nothing to solve for. We can just type that into our calculator. Let's go ahead and do that now. So negative log 3.16 times 10 to the negative 8. And we get approximately 7.50. And for those of you in the health sciences, you'll realize that's a pretty normal pH for blood. This is actually a reading from a sample of human blood. So as you can see, pH is actually a logarithmic scale. Let's look at another example. So suppose, now this is, at least to my knowledge, this is still correct. To my knowledge, the most acidic rainfall recorded had a pH of 2.4, and that was in Scotland, I think in the 70s. Maybe that's been beat, but last I checked a couple years ago, this record still stood. Compute the hydrogen ion concentration. So let's try the reverse. We know the pH. I want to know what's the actual concentration of the hydrogen ions in that rain. So let me rewrite the formula. And that's what pH is. We know the pH is 2.4, so set the pH to 2.4. What we don't know is the hydrogen ion concentration. So we need to solve this. So first thing we need to do is isolate the logarithm, and then change it to an exponential. Right? That's the trick. How do you solve logarithmic equations? Loosely speaking, you'll change them to exponentials. So that's a base 10 logarithm. We got the common logarithm there, so it's going to be 10 raised to the negative 2.4 equals hydrogen ion concentration. Boom, there it is, all done. So as you can see, working with the pH scale, pretty quick and easy. And there's many more logarithmic scales for a variety of phenomenon. The one I'm going to provide here is the decibel scale. So that's written there for you to reference in your homework, but there's just really two variables. B, which is sound intensity in decibels, and I, which is sound intensity in watts per square meters, which is the actual measurement from the sound wave itself. Alright, last topic here, logistic growth models. Looking at logistic growth models. The logistic growth model appears exponential at first, but then it's going to start to taper off as it approaches its carrying capacity. So these are very useful in biology. Right? You might have an organism that finds the perfect habitat where conditions are perfect, so it's going to grow rapidly, but as it grows, there's only so many natural resources in that habitat, and it's going to approach what's called a carrying capacity. The carrying capacity is, the highest capacity of organisms that habitat can carry, because then eventually it's just going to run out of resources. So a logistic growth model is useful in biology, but it appears in other applications as well. Looks like that. Now, if we look at that model, x is your variable, a, b, and c are all constants, and I want you to pay close attention to this constant in the numerator, marked by a c. That's the carrying capacity. I think you have a problem in the test review where it asks for the carrying capacity. It's just the number in the numerator. So easy to identify. And then the graph looks something like this. So at first it looks exponential, but then suppose as you start to run out of resources, that rate of growth is going to decelerate, and it's eventually going to start flattening off to the carrying capacity. All right, that's a wrap. So we are done with Math 1111 lectures. Guys, that was our last lecture of the class. So just got one more test review, one more test, and then comprehensive final. So we are at the tail end of the class. So keep up the hard work for just a little bit longer, and then you can have a nice little break. So keep up the hustle, guys.